So we are starting with conjugate heat transfer. So what are the modes of heat transfer? So we for the people who are not familiar with heat transfer, there are three modes of heat transfer. First is conduction, second is convection, and the third is radiation. For conduction, there has to be physical contact between the two materials, or the material will be solid in nature, like when there is no transport of the particles. But convection happens in fluids when there is bulk motion of the fluids. So you can look at this example. So whatever heat is being generated by the stove is going either by convection or radiation to the pan, and from there the heat is being conducted through the solid handle and then to the person who's holding it. But the inside the water, whatever heat is being generated, it is recirculating or it is moving and causing motion within the fluid, and that is convection. Radiation is the mode of heat transfer. Hmm, wherein there is no medium in between. So how the energy comes from the sun to us, that comes via radiation, because there is no medium, there is complete vacuum. So these are the three modes. So now conjugate heat transfer is a combination of both heat transfer due to conduction as well as convection. So under which applications do we encounter conjugate heat transfer? So first is, you can see CPU cooling. So your CPU that is being cooled is generating the heat, and that heat is getting spread by these fins and distributed, and then cold air is circulated over this. So there is heat that is first being conducted through the solid material and then convected through the air. So generally, in all the applications, you will not have only pure conduction, you will not have only pure convection or radiation, but you will always have a combination of these. That is where conjugate heat transfer simulations come into picture. And the second application you can look at is the heat exchanger. In heat exchanger, always there is a hot fluid flowing through one side. So in this case, the hot fluid is flowing through the tubes, and the cool fluid is flowing through the shell. So heat is being transferred from the hot fluid through the tube material and then to the shell fluid. So in this way, there is convection, conduction, and then again convection. So this to solve this, you need to go for the conjugate heat transfer class of solvers. Okay, so the geometry that we are going to look at today is, basically we thought that, okay, let us simulate one practical case. So we were thinking of simulating the temperature rise in a magnetic core. So the magnetic core of a transformer gets heated during operation. Okay, and that heat needs to be dissipated to the environment for safe working. Otherwise, that core will melt. So for that reason, what we are doing is we are taking a simplified form of the core. Generally, core will have some hollow patches, but we are considering that to be solid for obviously ease, so that we are able to mesh it quickly and demonstrate. But in practical cases, the core will also have what you can say hollow sections. Now this core is 50 mm wide, 30 mm tall, and 10 mm in thickness. And we are considering the working fluid to be air. The air velocity we are taking as 0.01 meter per second. And these are some of the properties of the solid core. Now, if you see, we have the core, but we also need to decide the computational domain. So we will have to keep the core somewhere in the center of the computational domain, and we would need to have a fluid that is around it. So in the fluid, the equations for the fluid will be solved. In the core, equations for the solid will be solved. We need to create a mesh, something like this, to be able to solve CHT. Now, this can be done in multiple ways. Because this is a simple geometry, we can do this mesh very easily using the toposet utility. That is good enough for basic geometries. But today we wanted to demonstrate to you the snappy hex mesh dict. So whenever you have complex geometries and you want to place them inside a fluid domain and mesh them, snappy hex mesh is a very good candidate. Or then you can also go for third-party applications. You can mesh in any of the desired measure that you want, and then you can import it. Like OpenFOAM has the capability to import mesh from Fluent, so you can import even Fluent mesh using the command Fluent 3D mesh to foam. So now we have understood that if the geometry is complex, there is need for advanced meshing. So I will hand over to Evan, who will demonstrate to you how SnappyX mesh works, and he will mesh this domain. Once the meshing is done, we will move ahead with the case setup. Okay. So I will hand over to Evan.